Hey guys, my name's Jack.
Hi, Jack. Hello.
I'm a student here. I do red team, blue team, black team, pen testing, REV, RIoT, and malware and stuff. I'm going to talk to you guys today about rootkits. Real quick, how many of you guys are blue teaming this year? Cool. How many of you specifically are interested in going to University of Buffalo in November? Yeah, pull them up. All right, cool. Pay attention. So a rootkit is used What's up, Quentin? I outsourced. I delegated. Is it not doing it?
Mm-mm.
Please hold. Yeah, I know, right? I'd start telling jokes, but
Hey, we should all talk about how Facebook just got hacked.
we can. Is it up yet? Yeah, try reconfiguring it. All right, well, yeah, it's also just really warm and fuzzy. But anyways, so rootkits are something I've been working on for the last year or two. This is specifically a talk about Linux kernel module rootkits. The Linux kernel is what is inside of Linux and what makes Linux Linux. So Ubuntu isn't Linux. Ubuntu is a distribution that uses the Linux kernel. The kernel is what interacts with everything. So as you, the user, use your computer, you run programs like ls, if you're catting a file, anything like that, you're using the kernel. All of your network stuff, kernel. Files, kernel. Everything goes through there. So this is why it's a really great place to put a malicious tool. How's it look, Quentin?
Get it onto the screen. Good. There we go.
Is it good? Cool. So TLDR, a rootkit hides the bad guy's tools. Since we're going to kind of go with a superhero theme, we're going to try and stick with superhero metaphors. So here's our kernel. The hardware sits behind the kernel. Hey, Quentin, are you following me? The kernel interacts between the userland and the kernel. So when you run a program, it talks to the kernel to get access to the hardware. So a good example might be a printer. When you say print, you're sending data to the printer and you're saying, I want this to go on paper. So the printer takes it and interprets it. And it says, OK, I have this character and I have to move the read head or the write head this way in order to create it on the paper. So the kernel is interpreting the document that you sent and putting it down on paper. A malicious actor might take that, inject themselves into the kernel, and say, OK, I don't want them printing these words. So if I see the word Jack, I'm just not going to print it. So that'd be an example of a kernel module rootkit doing something. Here's a Linux example of how the kernel works. So when you echo hello to your terminal, this is what's actually happening. strace is a tool that shows you the system calls. So every call that goes to the kernel gets printed out. So right here, we have a call to exec-cve. That means that we're executing this binary, /bin echo. It does some other stuff. It's reading some files, allocating memory, opening cache. And it reads the binary file here. So you can see the elf header over there. And then it's writing to the screen. And so those are all the system calls that you have access to when you're in the kernel. So the first technique we're going to talk about is directly overwriting the system call table. In the kernel, each one of those calls that you just saw, write, exec-cve, mmap, all of those are system calls. And they sit in a table. And when you want to execute one, the kernel goes and it looks it up. It says, OK, here it is. And it follows it over. And that's what it executes. So as you can see from the diagram, I have my table and my little pointers pointing over to executing code. And now when I insert a malicious kernel module, I go through and I overwrite this one. I say syswrite doesn't point over there. Syswrite points to my code. It points to evilwrite. And so this way, when they're writing code or writing text out to the screen or to a file or anywhere, I can say, I don't like that word. I'm not going to print that word. So if I'm trying to redact my name from everything, I don't want Jack McKenna written anywhere. I just say, are you going to print Jack McKenna? If so, we're not going to print at all.
Could you replace it with Hulto?
I could. That'd be great. I'm gonna do that on all your boxes. Pro cons of doing this, you're able to hook system calls. It's pretty hard to find. It's really hard to remove, especially without restarting. I think the only way I have to do it is to restart your computer. Cons, it's a little complicated getting started. You have to figure out how to write a kernel module. Once you get into it, it's pretty easy though. And it's system dependent. So it's going to depend on what version and subversion of the kernel you're running to some extent, but not a whole lot. And this is a little more complicated. This is inline system hooking. So instead of just replacing that pointer to where we're executing code, we're actually overwriting the system call's code. So here, we're going to overwrite syswrite. So we go over here. In here, we overwrite this code down there, the original code of syswrite, to jump over to our code. And then we execute our malicious stuff. We do our checks. We say, is this Jack McKenna? If so, replace it with Hulto. And then we jump back around to the original. So it's like nothing ever happened. This is a lot harder to find. With the original, just replace the syscall in the table code. You can kind of go through and say, is this the same as when I started my computer? Has it changed? You can do some checks. With this, you actually have to go through and check the integrity of each function. And you can hook in different places. So you could hook at the end of a function or at the beginning of a function. And so they have to check the entirety of each system call. It's very hard to remove. You also have to restart. It's about the same difficulty as the other one, though. But this one's very, very, very system dependent. We found that it depends on the major, minor versions of your computer. It can depend on the compiler that was used to compile your kernel. And it also depends on which distribution of Linux you're running. So you could be running the 4.17 kernel on Ubuntu and Debian, and they would have different system call instructions because we're working at the assembly level here.
How do you solve that problem? The problem with like the...
Oh, so the way that you would go about solving the compatibility issues between different distributions, subversions, and major versions is using a tool called an LDE, which is a length disassembly engine. So we're going to automate the hooking function because right now it's manual. So you go in and you disassemble parts of the kernel and you say, okay, there's a byte cut at 14 bytes, which means that I'm not going to cut an instruction in half. Because if you cut an instruction in half and then you jump back to it, the computer's going to say, I don't know what the hell this is. Help, 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 and just kind of die. With an LDE, you can say, this instruction is this many bytes long. We're going to end at the end of that instruction, copy all of that, and replace it. So in order to remove one of these, enforce module signing. So some modules are signed, like IP tables is a kernel module. That's signed by the developers. The kernel has a key store in it, and it says, and it checks each module that gets loaded. So if you load an unsigned one, it'll say kernel's been tainted, but it'll let you do it. If you enforce kernel module signing, it won't let you load unsigned ones. So what you do, go to your grub config, add this line, enforce kernel module signing, update grub, and reboot your computer. Are there other kinds? You betcha. There's LD Preload and Backdoor Binaries are the other two really common ones. LD Preload is a userland one where you're basically backdooring the libraries that functions use. So in Java, have you guys ever worked with the like the overwrite thing where you can put override? Yeah. So in Java, you can override functions from the superclass in your child class. This is kind of like that. You can override the library's original functions. So if you want to, let's say fprintf, you want to overwrite fprintf. You just define fprintf in the LD Preload shared object library, and then you make it do whatever you want. And then, yeah, that's how it works. It's pretty easy. They're pretty easy to find. There's an LD Preload environment variable that you can change, and an LD Preload shared object file that you can change. If you check those, you'll be good. Otherwise, backdoored binaries. This is pretty hard to find, or just tedious, because you have to go through and check the integrity of every single binary that you're going to use. Have fun with that. Are there any questions about anything? What's up, Stuart? There are some. I haven't found any that work. What's up?
Would it be possible to replace entries in the kernel key store so that a self-signed certificate would show up as if it was properly signed?
So, maybe. And so Stuart's question was if there were automated tools, and I said yes, but they don't really work. What's up, Rain?
I was saying, what was the other one?
Oh, Quentin asked about updating key stores once you're in the kernel.
Oh.
And I said maybe.
Is there any other language?
Yeah, probably. Are you getting at something, Rain? Okay. There are other kinds that I haven't covered here today. I just don't have a lot of time or knowledge on them. Anyone else have questions? You can ask me anything. About UB? Yeah. All right, cool. Thanks for your time, guys.